Welcome to the solutions to the Regents Physics Kinematics problem set, problems numbers 24 and 25. This is a set of problems that switches direction for us. Most all of the problems that we've done thus far in our study of one-dimensional motion have been horizontal. So all the objects have been traveling sideways. We now switch planes here, and now our objects will be traveling vertically in one dimension, which of course takes into account the acceleration due to gravity that we need to take into consideration when objects are either traveling up and slowing down or traveling downward and accelerating. All right, let's start with 24. Suppose an astronaut drops a feather from 1.2 meters above the surface of the moon. This would be the distance or displacement. If the acceleration due to gravity on the moon is 1.62 meters per second squared, so this would be the acceleration, which acceleration due to gravity is given a special symbol, little g. How long does it take, and that's time, the feather to hit the moon surface? Okay. The other key piece of information in this problem is the word drops. Anytime we drop an object, we know that its initial velocity is 0. Okay. Before we proceed and solve this problem, I want to show you a quick little video on this actual event. If you've not seen the footage, this is from Apollo 15 and the actual experiment where they dropped a feather and a hammer from the same height near the surface of the moon, and let's see what happens.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got it from a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? My conclusion that Mr. Galileo was correct in his findings.
Really neat demonstration that shows that all objects disregarding air resistance fall the same regardless of their mass. Both the feather and the hammer hit the moon's surface at the same time because there was no air resistance, there's no atmosphere on the moon. So both fell at the same rate and hit the ground at the same time. Really neat demonstration on the surface of the moon. All right, let's continue this problem. As we take a look at it, and we are looking for t, and we have an initial velocity 0, a distance, and an acceleration, we go to the reference table to appropriately select an equation that will help us get the answer. And it looks like we should select d equals VIT plus 1/2 AT squared. 1.2 meters is our displacement. Our initial velocity is 0, so the entire VIT term is 0, since 0 times t would be also 0, plus 1/2 1.62 meters per second squared times t squared. So we go ahead and we solve for t algebraically. Take whatever steps you need to accomplish this task. The biggest mistake in solving for t in this calculation is forgetting to take the square root after you've manipulated the 1/2 and the 1.62 over to the other side. Don't forget to do that. Pause the video if you need time to do your calculation, and your answer should be 1.2 seconds. Okay, so there you go with your answer to number 24. Okay, moving on to 25. We have a stone that starts at rest. So that means its initial velocity is 0. In free fall, that indicates to us the acceleration is acceleration due to gravity, which is 9.81 meters per second squared for 8 seconds. And that, of course, is time. Calculate the stone's velocity after the 8 seconds. That would be its final velocity. And what is the stone's displacement during that time? And that, of course, would be the d value. Okay? All right, so for A, we're looking for VF. So knowing VI is 0, our acceleration and our time, what makes sense here? It looks like as we inspect the reference table, we should use VF equals VI plus AT. VF equals VI, which is 0, plus 9.81 meters per second squared, acceleration due to gravity, times the time of 8 seconds. And doing our math, we should end up with a final velocity of 78 meters per second. For B, you want to know the distance traveled. Once again, going to the reference table. With the given information, it looks like we should select D equals VIT plus 1/2 AT squared. Once again, initial velocity is 0. So 1/2 9.81 meters per second squared times our time of 8 seconds. And don't forget to square that value. Go ahead and do the math. And we get an answer to 2 digits of 310 meters. Okay? Both answers to 2 digits because our time is our only measurement and it was to 2 digits. We never use a constant or accepted value. We only use measurements in determining sig figs. All right, more on one-dimensional free fall problems in class tomorrow.